From simple harmonic motion of a spring to the electromagnetic force, Newton's laws of motion describe forces using second-order differential equations. From classical mechanics to electrical engineering, solving second-order differential equations has always been a tedious and sometimes unforgiving process. Which is why this year I'm thankful for Laplace Transforms. Consider solving the second-degree polynomial equation x squared minus 10x plus 9 equals 0. The theory of solving equations has been a central theme in mathematics, and especially in high school mathematics. For instance, to solve this equation, one might try writing it in factored form, x minus 1 times x minus 9 equals 0. And setting each one of those factors equal to 0 to solve for x is applying the zero product rule. Now, for solving algebraic equations such as this quadratic, there are many different methods that can be approached here. For instance, factoring is not the only way we can do this. Applying something called the quadratic formula, which is a form of completing the square, is relevant to solving algebraic equations, because we use algebraic operations to create them. Now, a family of equations that prove very difficult to solve in calculus are differential equations, equations that contain derivatives or rates of change. Moving from the realm of the discrete to the realm of the continuous is where we apply calculus, and this is where things about solving equations take a turn for the interesting. The derivative of a function f prime, df dx, can be defined in its limit definition. Here, we'll use the function y of x, or rather y of t, where t is a continuous variable. Here we'll use y prime for the first derivative and y double prime for the second derivative. Now, a differential equation will often contain derivatives of many different orders. The higher the order of a differential equation, the harder it becomes to solve. Here we'll focus our attention on second-order differential equations such as this one, y double prime minus 10y prime plus 9y equals 5t. The goal in solving such a differential equation is to find the function y of t. And we'll see that we'll use an integral transform to make our lives easier. But first, to see why it makes our lives easier, we're going to have to go through a brute force method of solving such an equation. This year, I'm thankful for integral transforms. And you might be familiar with a few of them. One famous heavy hitter is the famous Fourier transform. But today, I'll be focusing on one of my favorites, the Laplace transform. The Laplace transform takes a function of a variable t and transforms it into a different function of a variable here s. Integral transforms are often defined by indefinite integrals such as this one. Isaac Newton was the one who helped lay down the foundations for calculus and classical physics with his laws of motion. They were later then progressed into understanding the laws of electromagnetism. And a central theme are forces, where we can understand force by understanding first how perhaps a spring works. So a spring is a restoring force. And using Hooke's law, we can relate this to the proportional constant k, negative k times x, x being the distance that the spring is moving. So force is equal to mass times acceleration, or mass times the second derivative of position with respect to time. And setting that equal to this proportional value negative k times x, we create a second order differential linear equation. And this would be an example of a homogeneous equation because it is set equal to 0. Now, studying springs and the way that those differential equations describe the laws of motion, we get general solutions which describe what we call simple harmonic motion, oscillations that we see in nature. And we can describe these things pretty accurately because of the fact that we've been able to solve these differential equations. Differential equations are the bread and butter of math and physics at the most highest level. Now, even applying an external force, or a dampening force, to the spring, we can create another second-order differential equation, one that is non-homogeneous because the right-hand side is equal to a function that varies with time, an external force. We can also liken this to the ideas given in electrical circuits, where we have a resistor, an inductor, a capacitor, a battery voltage, and a switch. And using something called Kirchhoff's law, we can write down a few equations here that will give us some differential equations to solve. Q stands for a charge, and a charge moving through an electrical circuit. Voltage provided by a battery will experience voltage drops throughout the circuit at each of the resistor, the inductor, and the capacitor given here. And since the sum of the voltage drops has to equal the total voltage given by the battery, we have Kirchhoff's law giving us the voltage, and this equation here is a first-order differential equation. But because I, the current in this particular circuit, is the rate of change of the charge, we can rewrite this as a second-order differential equation, relating the electromotive force, E, to the circuit here. And you can see the parallel to the non-homogeneous equation we had for the spring. And so there's a lot of physics that can be mined here, but we're going to focus in general on how to solve second-order differential equations such as this. And we're first going to go through it in a brute force method so that we can appreciate how an integral transform such as the Laplace transform is very helpful in solving such equations. Consider the initial value problem of this second-order differential equation with the initial conditions given. Pause the video now if you'd like to try to figure it out. Since our goal is to find the function y of t, we begin by solving the homogeneous equation, that is the equation set equal to 0. Since we have a lot of knowledge on how to solve algebraic equations, what we're going to do is apply something called a differential operator, d, capital D here, and rewrite this equation using an algebraic type of form, using a characteristic or auxiliary equation. And since we can factor that characteristic equation, we can get a general solution which is of the form c1 e to the t plus c2 e to the 9t. And that is because each of those separate parts are separable equations. And if our general form of our homogeneous equation has this form, we can also write down its derivative and use the initial conditions to find the coefficients c1 and c2. And with solving a little bit of a system of equations here, we get c2 to be 3/8 and c1 to be -11/8. So substituting those back into our general equation for the homogeneous solution, we'll get a general idea of what the answer is going to look like. And so this is one of the first methods that we use to solve a second-order differential equation. So here's the homogeneous solution. Now the solution to our equation will be a combination, a linear combination of the homogeneous solution and a particular solution. So the particular solution is with this equation equal to 5t, And we're going to apply that differential operator here, and then we're going to let u be d minus 9 equals times y, and use that to create a first order differential equation that we can solve in terms of u. What that does is it allows us to pull out something called an integrating factor, here e to the negative t. And what we do is we multiply both sides of the particular solution equation with this integrating factor, and what it does is it allows us to rewrite the equation in a nicer form, a more solvable form. So let's take a look at what it looks like to multiply both sides of our particular equation with this integrating factor. And by doing this and rewriting it and rearranging it, we get u is equal to e to the t times an integral 5t e to the negative t dt. So what we can do is we can solve this integral using a little integration by parts, and then we'll have an expression for u here, negative 5 times t plus 1 plus a constant a e to the negative t. And since u was equal to d minus 9 times y, we then can solve another first order differential equation in terms of y by finding another integrating factor by solving the homogeneous case. Here the new integrating factor is e to the negative 9t. And then multiplying that on both sides of our particular equation, and we are going to then get y is equal to the general form of e to the 9t times this integral that we have to evaluate. Now these integrals that we're trying to evaluate here aren't particularly hard. We can do again some integration by parts to treat this, and this is all something you'll find in a second year calculus class. So we get a general form for y, the solution to our differential equation, and we have a couple of constants in there, a and k, to solve for, to use the initial conditions to give us the particular values for those. Alright, so let's take a look at what that looks like. We have the a and the k to use, and in this equation we just apply the initial conditions, we get those values, and we get the particular solution to our differential equation. And so you can see it's pretty involved to use the brute force method of solving this differential equation. And because of the fact that these types of equations show up in classical mechanics, people have been devising simple machines to help us solve some of these problems and understand them. And integral transforms are a type of machine that I am very thankful helps us solve a second order differential equation. So the Laplace transform defined here, you might see the curly L notation for this. It's going to take a function f of t and transform it into a capital F of s function. So you can see a lot of different examples of how to calculate the Laplace transform for different families of functions. And so if we were to apply the Laplace transform to a function y of t, we would get a capital Y of s. And you can see that if we applied the Laplace transform to a derivative y prime, we could write this out in terms of capital Y of s and the variable s, and also our initial conditions. So the Laplace transform, we can devise expressions for y prime and y double prime. And what that's going to allow us to do is apply a Laplace transform to the entire differential equation because it is a linear operator. So let's put this all together. We're going to apply the Laplace transform as a linear operator to our entire differential equation, break it off into separate pieces, and then evaluate each piece separately. And then we'll get an expression in terms of y, capital Y of s. So applying the linear operator here, separating our pieces here, then we just have to rewrite our Laplace transform for y double prime, y, and 5t. And plugging those expressions in that we talked about earlier, we can write capital Y of s in terms of a rational expression. And to get little y of t, we're going to have to integrate or apply the inverse Laplace transform. So therefore, we would like to have a nice partial fraction decomposition of this particular function. Sparing you all the details here, we would then apply what's called the inverse Laplace transform to get our final solution, y of t. And the inverse Laplace transform, you can make a table of Laplace transform values and use that table to get the inverse Laplace transform solutions. So there you have it. It's a power tool that I'm thankful for this Thanksgiving. And I hope you have a happy Thanksgiving. Please hit that like, subscribe, and notification bell for more videos, and stay tuned.